And with that, let me introduce our presenter today. Our presenter today is Jeff Forage with the National Bobwhite Conservation Initiative Grassland. He is the National Bobwhite Conservation Initiative's Grassland Coordinator. And with Jeff, I'll turn it over to you to begin the presentation.
All right. Thank you, Bob. I'd like to start out by thanking Dr. Garden for his help today and helping me get organized and set up with Collaborate, and also recognize the Southern Region Extension Forestry for hosting this webinar. Well, welcome, everyone. I'm glad you're able to join me today. I hope you find the information I'll be presenting useful. I want to start out with just a brief background about the National Bobwhite Conservation Initiative, in case some of you may not be familiar. The National Bobwhite Conservation Initiative is a unified multi-state initiative to restore wild bobwhite quail to America's landscape, and we're headquartered at the University of Tennessee Institute of Agriculture in the Forestry, Wildlife, and Fisheries Department. NBCI was created by the state fish and wildlife management agencies, comprising the core of the bobwhite range, and it's funded by those agencies. In addition to that, the University of Tennessee, Park Cities Quail, and the Quail and Upland Game Alliance. NBCI is charged with developing and coordinating the implementation of a national habitat-based approach for the landscape scale restoration of wild bobwhites. So why is NBCI interested in native vegetation? Well, native vegetation is widely promoted for wildlife applications, but it's less frequently used for other conservation uses. So one of the key strategies of NBCI is increasing the awareness and the adoption of native vegetation for all conservation practices and incorporating native vegetation into working lands, particularly forage systems. NBCI is also currently leading an effort to create a greater emphasis on native vegetation in the Farm Bill under the banner of Natives First. So in today's webinar, I want to point out that this is not a presentation of original research conducted by myself or NBCI, but it's a review and a compilation of research which has been conducted throughout the tallgrass prairie in the southeastern United States. And the handout provided with today's presentation provides references that I'll be using throughout the presentation, so you won't need to worry about trying to jot those down. You can go to that handout and have access to those. So the first thing I want to do is review some commonly known facts about the root systems of native vegetation to establish some background and also create an understanding of how these native vegetation perform many of their ecosystem functions. And for organizational purposes, I've tried to separate out those ecosystem functions by category, but many times they're so interconnected it's difficult to make clear distinctions between them. So you will notice some overlap. We're going to take a look at their roles in soil conservation, water quality, air quality, soil health, forage, biomass, and then briefly take a look at wildlife. And then where possible, I'll make comparisons to the commonly used non-native plants, and then I'll wrap up with some economic comparisons between the natives and non-natives. An important point to make before I get too much further into that is that native plants are adapted to their local adaptive climatic and physiological conditions, so is that associated soil biology. So creating this symbiotic relationship. So when non-natives are introduced, they have to build their own specific soil associations, and likewise, when non-natives are converted to natives, that process has to begin again. And there has been some thought to the idea that may be why, when seemingly everything else is equal, that some native plantings aren't as successful as others. Now in this slide, we're taking a look at some of the root systems of some common native plants. I'm sure you've all seen the graphic representations. These are some photographs from Jim Richardson Photography, which were taken near Salina, Kansas at the Land Institute. And looking at these from left to right, we've got big blue stem, little blue stem, rosinweed, Missouri goldenrod, prairie cordgrass, switchgrass, and intermediate wheatgrass. Also point out intermediate wheatgrass is a non-native, but it is included here. As you can tell by looking at these, most of these root systems are fibrous, but some of the forbs do have a dominant taproot with lateral root systems. So we take some examples of rooting depth from Weaver's book, North American Prairie, for some species of native grasses, including both warm and cool season. And you can see that ranging from 1.5 feet deep with the cool season June grass to 11 feet deep for the warm season switchgrass, these grow quite deep. Now, of course, these rooting depths also depend on soil type, fertility, and some other factors, so there is some variability in that. And we look at some of the forbs, you can see that these depths run from 5 to 16 feet. So for the most part, forb root systems run much deeper than the grasses do. And one little tidbit I want to introduce here is that most native forbs, though they may be warm season, are C3 plants, as are the cool season grasses, while the warm season grasses are C4. So to wrap up this review about the root systems of native plants, as much as 70% of the biomass produced by native plants is below ground. And Weaver, studying these roots in tallgrass prairie, Nebraska, and Iowa during the 40s, documented that the greatest biomass of roots was in the top 12 inches of soil, and that depending upon the species, as much as 1/3 of the root biomass died and was regenerated annually. And in this slide, you can see that in the upper 12 inches, big blue stem produced 5.4 tons per acre, little blue stem 4.4 tons per acre of root biomass. Now think of that root biomass and this process of these roots dying and regenerating on an annual basis, and what impact that would have on soil organic matter, soil tilth, infiltration, soil biology, and the water holding capacity. Okay, so now let's move on and take a look at some of the ecosystem services related to soil conservation functions of vegetative cover, and I might point out any vegetative cover that's not unique to native grasses, is the interception of rainfall. They either dissipate the energy of that falling raindrop, or they're keeping them from directly, they keep them from directly impacting the ground. Clark, in a 1940 study, found that big blue stem intercepted from 47 to 84% of the rainfall, and that was dependent upon the intensity of the rainfall and what season. And then Weaver found that native vegetation in tallgrass prairie held anywhere from 50 to 97% of the rain. Again, that had to do with the intensity of the season. And that was a function of leaf surface area, the physical structure of the plant, but not only plant, the plant community affects that rain interception. Taller plants would intercept more than the shorter plants, and multiple layers intercept more than single layers. So diverse plantings of forbs and grasses provide multiple layers, and those that are growing in regions receiving above about 25 inches average annual rainfall are typically taller than the common non-native plants used for conservation. And looking at filter strips in particular, in a collection of papers and newsletters by Grimshaw and Helfler, they revealed that stiff stem grasses were resistant to hydraulic pressure, and that stem resistance dissipated energy and encouraged ponding, which in turn increased infiltration. Lee et al. Found that sod-forming grasses collapsed under high water pressure and in concentrated flow channels. In that condition, were unable to slow water flow. Now, I should point out that the Grimshaw and Helfer report was on vetiver grass, which is a native of India, but their findings were presented here to help illustrate the function of the stiff stem grasses. Dillaha suggested that short, cool season grass filters might lose their effectiveness when they became inundated with sediment, and Dabney et al. Reported that because of hydraulic resistance of stiff grasses, they were better at slowing water velocities than finer vegetation such as tall fescue and Bermuda grass. And Dabney also showed that switchgrass is not easily covered with sediment and therefore maintains its effectiveness for longer periods of time. Lee et al. In one of the previous studies that I'd mentioned found that 6-meter wide switchgrass filter strips, when compared to 6-meter wide filter strips of a mix of brome, timothy, and tall fescue, that the switchgrass filter strips were most effective at trapping sediment from surface runoff, and the amount of sediment trapped in those filters was higher than reported in other studies of cool season filter strips by Maggette and Parsons. Going back to that Grimshaw and Helfer publication, and again, this was vetiver grass, but it's used as an illustration of what deep root systems do. They reported that a deep fibrous root system acts to prevent slope failure. And think about this for a minute. If you've ever poured concrete for a wall or a slab, what did you put in that to strengthen it? Well, you either put in rebar or wire mesh. And these fibrous root systems act just like rebar and concrete, strengthening the soil. Now, if you're old enough, you may remember the great flood of 1993 that devastated the Missouri and Mississippi rivers. And being from Missouri, I was able to observe a lot of that aftermath of those floods, where they had overtopped levees, and where some of those sections of those levees had survived because of switchgrass cover, where adjacent to those were breached. One of the reasons for that was the tall structure of the switchgrass laid over with the water flow and it armored the levee surface. And then secondly, the root systems of the switchgrass held the levees. And where this was most evident was where switchgrass and other grasses were adjacent to each other, where the non-native section had washed out, and you could see that the tremendous amount of root system into that levee bank right next to the section that held out. So it really wasn't hard to imagine why that section held while the other sections washed out. Now let's look at sediment reduction. Again, this is looking at either filter strips or buffers. Schulte et al. Found that prairie vegetation strips, and also Lee et al. Looking at switchgrass buffer strips located at the lower end of the test plot, and both of those studies found that they reduced sediment by 95%. Now, Lee et al. In a different study, but one we referred to earlier, comparing the 6 and 3 meter wide buffers of switchgrass and same size mixed cool season buffers, the switchgrass buffer removed 5.5% and 11.3% respectively for their width, more sediment than the cool season buffer. Now those may be a little bit confusing because you'd think that the wider buffer would remove more or create a bigger difference. But what this shows is that the larger buffers, both of the larger buffers were effective at removing sediment, but the narrow buffer of switchgrass is significantly more effective than the narrow buffer. And therefore they take less area, less buffer area required with switchgrass, means less grounds taken out of production. Well, in Iowa, in its buffer standards, they require their cool season grass buffers to be 2 times wider than the native grass buffers. It's a good illustration of those benefits. Also point out, you see at the bottom of the slide here a reference to STRIPS project, Iowa State University, and again, that link is reported in the handout that's with today's presentation. So you could go look. There's a mass of data and studies that have been done in relation with this project, and a lot of these research papers that I'm including today come from that. So let's look at nutrient removal. Again, back to Lee, and it's pretty common for these studies to include sediment and nutrients all together at the same time, just because of the convenience of both of those. A lot of those are carried in those coarse sediments that are carried off in the water, so it makes them easy and convenient to do both of those studies at the same time. So looking at the nutrients again, in that same study that I talked about a slide or two ago about Schulte, she had found 77% less total nitrogen and total phosphorus in the surface water from those prairie vegetation strips compared to areas without prairie vegetation strips. And in that 1999 study by Lee et al., comparing the 6 and 3 meter wide switchgrass and cool season buffers, the switchgrass buffers removed more total N and total P in all instances, regardless of the width. So take another look, and this is another results from a study conducted by Lee et al., and he looked at 23-foot wide switchgrass and 53.5-foot wide switchgrass woody buffers. And in all cases, the combination buffer, the switchgrass and the woody buffer, reduced a higher percentage of nutrient concentration. However, Lee hypothesized that a switchgrass only buffer that was 53.5 feet wide might perform similarly, or perhaps even better, because a majority, well over 70% of the nutrient reduction was in the switchgrass portion of the mixed buffer. Now looking at water quality and pesticides, Leidick et al. Had found that prairie vegetation strips led to 68% lower concentrations in neonicotinoids in groundwater and 96% lower concentrations in the soil when these measurements were taken at the foot slope, and then anywhere from 37 to 100% less in surface runoff. And again, that variance in that 37 to 100% had to do with the intensity of the rain event, how much water was flowing across the land and how fast. So continuing to look at pesticides, Belden looked at phytoremediation by prairie grasses, and in this case he was using big blue stem, Indian grass, and switchgrass, and included 4 of the common agricultural herbicides: atrazine, allichlor, metolachlor, and pendimethalin. And atrazine and allichlor degraded rapidly, and the metolachlor and pendimethalin were significantly reduced compared to controls. And these were done in container-grown situations, so it was vegetated versus non-vegetated, and the grass plants did photoremediate. I'll make that word up for this purpose. Photoremediate better than the untreated ones. So I want to kind of summarize here just a little bit because we went through a lot of different things, and I want to be fair. Filter strips, buffers, and I kind of use those terms interchangeably today, but any vegetative strip used for the purpose of filtering or buffering, they all reduce sediment, nutrients, and pesticides. These benefits are not necessarily unique to native vegetation. However, some of these studies have shown that these native vegetation filter strips remove greater amounts of sediment, more nutrients, and they function longer, as well as require less width to function efficiently than the non-native cool season alternatives. And in other functions, native vegetation performs at least as well. So I want to talk a little bit about air quality. Native vegetation sequesters more carbon than introduced grasses. Nichols et al. In a 2009 publication stated that data from their study of organic farming versus conventional farming practices indicated that arbuscular mycorrhizae fungi and glomalin may enhance carbon sequestration. In another study by Nichols and Millar, when looking at 6 different management systems, and those 6 were native grass rotational grazing, tame grass rotational grazing, tame grass heavy grazing, the 3 grazing approaches, and then conventional tillage plus manure, and long-term no-till. When looking at all 6 of those, the 3 grazing systems that had the highest glomalin concentrations, the 3 grazing systems had the highest glomalin concentrations, and the native grass rotational system had significantly higher values of those 3. So in another study by Nichols, looking at undisturbed soils under native vegetation in different locations, Maryland, Georgia, and Colorado, found that glomalin stored an average of 15% of the carbon found in those soils, and up to as much as 30%. So glomalin reduces the decomposition of unstable organic carbon compounds within the soil aggregates, and soil organic carbon is a major sink for atmospheric carbon dioxide and methane. So to kind of pull that all together, because there's more glomalin produced under native grasses and the impacts that has on carbon sequestration, we're going to take a very minor leap of faith in saying that native grasses would sequester more carbon. Now, I just read this morning, so unfortunately it's not in the handout, a study published a few days ago in Agricultural Systems called Impacts of Soil Carbon Sequestration on Life Cycle Greenhouse Gas Emissions in Midwestern U.S. Beef Finishing Systems. It was by Stanley and several other authors. Those authors were comparing greenhouse gas emissions from feedlots to adaptive multi-paddock, or sometimes called AMP grazing approaches to finishing beef. And what they concluded is that grass finishing beef using adaptive multi-paddock grazing could serve as an overall carbon sink. Now, in those studies, which were done in either Michigan or Minnesota, I don't recall, I believe Michigan, the AMP grazing was done on alfalfa, cool season, introduced pasture. But we can hypothesize that native vegetation would sequester more carbon due to the glomalin and soil aggregation, and the soil aggregation would make it resistant to release. So this discussion about glomalin, arbuscular mycorrhizae fungi, and soil organic carbon is a good segue into soil health. And excuse me for a moment, I need to take a drink. So looking at soil health, the glomalin plays a role in soil aggregation, which allows for better water infiltration, water holding capacity, gas exchange. It increases soil fertility by providing organic carbon to soil organisms, which use this food as energy to release plant nutrients from the soil. Now, looking at prairie vegetation strips and cropland, at the foot slope, Perez-Sarez in 2014 found a 37% increase in soil organic carbon and an almost 100% increase in total nitrogen. So soil organic carbon holds the water and the nutrients, reduces the risk of erosion and degradation. It improves the soil structure and tilth, and provides energy for soil microorganisms. Averill and Sims looked at prairie grasses as a remediation treatment to reduce polycyclic aromatic hydrocarbons in the soil, petroleum-based items. And they found that prairie grasses used in the study were able to phytoremediate, again, making up that word, of those polycyclic aromatic hydrocarbons from the soil. Kofeld et al. Found, looking at switchgrass, found that it had a greater shoot growth and more root biomass after 12 months compared to tall fescue, and that the switchgrass had greater polycyclic aromatic hydrocarbon concentrations. So we're referring back to our early discussion, 70% of the native vegetation is below ground. Up to 30% of that dies and is regenerated annually, and that significantly builds soil organic matter, which impacts the soil health. There's a growing body of research relating to soil health. However, there's not much of that that looks at the differences between the soil biology of native compared to non-native vegetation. Some evidence of better soil health with natives than non-natives is in a study from California by Coteen et al., which found non-native annual grasses cause a drop in soil carbon storage. So looking at what we know, it seems logical that at the very least we can say soil health benefits are as good with non-natives, but likely better. Now I want to shift away from ecosystem services and look at a little more direct benefit of natives. Looking at forage, and when we start looking at more direct benefits, it's a little bit easier to quantify what's going on. So native warm season forages provide increased summer production when cool season grasses are in a slump. As you're probably all aware, during the warm months, the cool season grasses slow down their growth or go nearly dormant, and that's just when the warm season grasses are beginning to actively grow. So we had numerous researchers that found average daily gains in the neighborhood of 2 pounds per day common through a 90 to 100 day grazing period. Kaiser et al. At the Center for Native Grasslands Management in Tennessee found that fewer acres are needed for hay production, with native warm season grasses typically producing from 1 to 3 tons more per acre than cool season grasses, and with lower inputs and fewer cuttings. Kaiser et al. In a different publication reports that generally speaking, native warm season grasses require 1/3 to 1/2 as much water and nitrogen to produce a unit of dry matter compared to tall fescue. Grazing native vegetation during the summer months allows producers to avoid endophyte-infected tall fescue during a time when the endophyte is most concentrated in tall fescue plants, and thus it avoids or mediates the effects of fescue toxicosis. And of course, the extensive root system and associated soil biology make native vegetation drought tolerant, providing forage when cool season and introduced warm season plants are dormant. And this is also an important consideration if climate change predictions are accurate. Looking at native vegetation as biomass, agricultural crops used for fuel production compete with food and forage uses, and therefore they drive up those prices. Well, native vegetation doesn't compete with food crops, and it eliminates that inflationary cycle caused by those competing interests. The native vegetation used for biomass are perennial, and they don't require any annual cultivation or planting. And Hopkins et al. And McLaughlin et al. Found that native grasses harvested for biomass yield from 4 to 12 tons per acre, and yields over 8 tons per acre are not uncommon. Jacoby and Jackson in 2000 reported that 95% of the carbon storage is below ground. So in a biomass harvest, it has a minimal impact on the stored carbon. Now, wildlife. I haven't provided any references for wildlife because, number one, it's widely accepted that native vegetation provides wildlife and pollinator habitat. And really, number two, wildlife's not the primary focus of this presentation. Native vegetation is currently being used for wildlife applications, and we're trying to promote its use for other conservation issues. But briefly, native grasses and forbs provide cover. Their seeds and leaves and plant parts provide food, and the native vegetation provides material for and/or structure for nesting or bedding. So I want to try to tease out some of the economics here. And one of the real issues is that there's a lack of research quantifying the value of ecosystem services in terms of soil conservation, water quality, air quality, and soil health provided by native vegetation. But there's a recent example of a water utility in Des Moines, Iowa, bringing a lawsuit against farmers because of increasing costs to treat water to remove sediment and agricultural chemicals, and that illustrates that soil conservation and water quality do have a direct value. Now, Helmers et al. Conducted a summary of buffer and vegetative filter strips research to determine an estimate of their value. The findings presented in their report, when applying estimated reductions to sediment, total nitrogen, and phosphorus to the National Conservation Buffer Initiative goal of 2 million acres, found a 4.1 cost to benefit ratio, and the value of water quality improvement was nearly $2.5 billion. They reported $2.495 billion. Now, the vegetation type wasn't identified, but the assumption can be made that a majority of the research buffers and vegetative filter strips were planted to non-native species, since that's the common practice. But knowing that, research demonstrates native buffers remove more sediment, nitrogen, and phosphorus, I think without much risk, it can be assumed that native buffers would have greater value than that. I want to look at some of the economics of forage. Again, we're in an arena that's much easier to quantify. And in this table, this is from the economic implications of growing native warm season grasses for forage in the Mid-South. It's a University of Tennessee Extension publication. Kaiser et al. Looked at production costs for hay, considering the inputs, the equipment and the labor, etc., and the yield. And when they looked at that, the big blue stem Indian grass had the lowest cost of production compared to Bermuda grass and Sudex, which Sudex is an annual warm season forage, and then also tall fescue. So the break-even points for big blue stem Indian grass was $53. For Bermuda grass, it was $75. For Sudex, it was $83, and for tall fescue, it was $123 per ton. Again, this would be what it costs to produce it. And hay prices are typically in the neighborhood of $50 to $65 per ton. So you can see that some of these might be a losing proposition. Now, what these lines represent are the range of the values. Right here, the range of the values, the stars are the average of what those values are again. So taking a look at it in just a little different way, and this also in the same publication, they compared the cost of gain for 3 summer forages. Again, it was native warm season grass, Bermuda grass, and Sudex. The native warm season grass was actually a big blue stem Indian grass mix. And again, I remind you that Sudex is an annual, so it has to be planted each year. So the cost per pound of gain was 31 cents for native warm season grass, 54 cents for Bermuda grass, and as you might expect, because it's an annual, 75 cents for Sudex. Again, these lines show a range of what those costs were, with the stars indicating what the average was. So during a season-long grazing trial conducted by the University of Tennessee, average daily gains for weaned steers was 1.6 pounds grazing on switchgrass and 2.2 pounds grazing on big blue Indian grass mixtures. So steers during that same time period grazing tall fescue gained approximately 0.8 of a pound daily. So there is, on the average, or in the neighborhood of a 1 pound per day difference in gain between the warm season grasses and tall fescue. So the economic implication is that at the end of the season, when you sell that animal, you have a couple of approaches. One, either the animal you sell is going to be heavier, you get more money, or you're going to sell that animal sooner and be able to start your cycle over sooner. And I've also previously mentioned that the advantage of grazing warm season grasses during those summer months is you avoid endified infected tall fescue. And it's estimated that the tall fescue or fescue toxicosis costs livestock industry about $1 billion in losses annually, just in reduced weight gain and animal performance. Let's look at some establishment. Now this table, again from that University of Tennessee economics publication, shows the payoff period for those same summer forages that we've been examining earlier, the native grass, Bermuda grass, and Sudex. And considering both the establishment and the maintenance cost, and using an average hay value of $65 per ton for large round hay bales, the native grasses began to provide a return investment in the 6th year. We're down here about the 6th year is where the native grasses provide a return in their investment. But whereas the Sudex or the Bermuda grass never did hit a payoff point. In fact, the further you go, the further you got away from a the longer you went, the further you got from a payoff point. So kind of keep that in mind as we talk a little bit more about establishment economics, that here we're looking at, with native grasses, a 6-year payoff or return on your investment. This table is based upon some calculations I made in June of 2016. And I might point out these are only direct costs. They don't include any labor or any other indirect costs such as equipment, insurance, amortization, any of those. So I'm assuming those would all be the same regardless of which of these plant materials you decided to plant. So the cost of tall fescue establishment is for conversion. I figured this based on a conversion of endophyte infected fescue to a novel endophyte tall fescue, which is a recommended alternative to replace that endophyte infected tall fescue. And the establishment method was the same for any of these, and that's a spray, smother, spray, and plant approach, which again is the recommended method for converting endophyte infected tall fescue to any non-infected plant material. So when you look at these costs over here on the end cost range, because of the need for nitrogen fertilizer, you end up seeing that actually big bluestem and switchgrass are less expensive than the novel endophyte, and only the Indian grass, which as it's represented here would be as a monoculture, is more expensive than the novel endophyted fescue. Typically, you would not plant these in a monoculture. You might switch grass, but usually bluestem and Indian grass are planted together, and when you would do a blend of those, then that price would be very similar to the cost of the novel endophyte fescue. So, to kind of give some validity to this, Kaiser, again at the Center for Native Grasslands Management, using some January 2011 cost, estimated out-of-pocket expenses for establishing big blue and Indian grass between $145 and $205 per acre. So a little bit higher than what I came up with here, but they're not outrageously higher. Now, Burdine, with the University of Kentucky Extension, estimated the cost of establishing novel endophyte tall fescue at about $206.50 per acre. And for comparison to other cool season forages, Iowa State University in a 2000 publication stated a range of costs depending upon the method and whether it was a grass or a grass legume mix, from $98.43 to $103.44 per acre. So you can use that for comparison. So native vegetation has been questioned due to its perceived high cost of establishment, but looking at the comparisons that we've just shown here, in some cases, but not all, establishment costs might be higher, but the improved summer weight gains in animal health should offset those differences relatively quickly. So I want to kind of wrap up here and then allow a little bit of time for questions. So results from Schulte et al. From a multi-year catchment scale experiment comparing corn and soybean fields with and without prairie vegetation and looking at the impacts on biodiversity and multiple benefits, indicated that the prairie strips raised pollinator and bird abundance, and they decreased water runoff and increased soil and nutrient retention. And these benefits accrued at levels that were disproportionately greater than the land area occupied by those prairie strips. So USDA subsidized conservation practices are public investments in private lands. And because society benefits from the conservation, those investments are a justifiable use of taxpayer dollars. However, if taxpayers are buying conservation services, shouldn't we get the most services for our investment? So we'd say that investments in native vegetation for conservation services provide a greater benefit than non-native vegetation, and therefore should be the preferred choice. That's all I have for today. Contact information is on there if you'd like to send me an email. And I guess, Dr. Barden, if you're ready, let's see if we've got any questions to follow up.
Thank you, Jeff, very much. And at this time, if you have questions, please type them into the chat window for Jeff.